When I introduced max flow and linear programming, a big part of the motivation I gave was that we could use them to solve other problems by reduction. So in this video, I'd like to give a couple of examples of designing algorithms by reduction, one where we reduce to max flow, and another where we reduce to linear programming. In general, when we talk about reductions, we mean translating an instance of one problem into an instance of another problem, so that solving the new problem gives us a solution to the original. Our example of a reduction to max flow will be building an algorithm to solve the disjoint paths problem. The motivation behind disjoint paths is that for some types of graphs, we might want to find many distinct paths from an origin to a destination. And if the reason that we're looking for many paths is that we want to have robust connections, we would like for those paths to not share any edges. This could come in very handy, for example, in internet routing, where we would like to have multiple completely separate routes that we could send data over in case one particular connection goes down. So we are given a directed graph along with origin and destination vertices, and we want to find a collection of paths from the origin to the destination such that no two paths share an edge and the collection is as large as possible. In this example graph, we can find 3 disjoint paths. Note that the paths can share vertices, but they cannot have any edges in common. And so at this point, we have used up all of the in-edges to our destination, so we know that there can't be any more paths that share no edges with these 3. At first, we might think to solve disjoint paths by graph traversal, but running several traversals and keeping the edges disjoint seems challenging, especially because if there is an edge that might be useful to several paths, it's not obvious which one it should go in. So instead, we will solve this problem by translating it into an instance of max flow. The first steps of our algorithm are to take the input that we are given for the disjoint paths problem and translate that into a valid input for the max flow problem. And we want to do that translation in such a way that the answer we get back from solving max flow will help us to solve disjoint paths. In this case, we are creating a graph G' that we will run max flow on. And G' has all of the same vertices, but we have removed any edges that come into the origin or come out from the destination. Those edges don't help us in finding disjoint paths, or for that matter finding flows, so it's fine to get rid of them. But in some sense, this step is superfluous. We totally could run max flow on the graph that contains those edges, and our algorithm would still work. The reason why I am doing this here is, 1, it will make our reasoning in the proof of correctness a little bit simpler, and 2, it illustrates the point that when we are doing a reduction, we are translating to a different problem. And so even if both of the problems, the original one and the one we are reducing to, are types of graph problem, we might still want to change the graph that we are giving as input to the target problem. The most important step in this translation is that to have a valid input for max flow, we need capacities for all of the edges, and we were not given capacities in the input to disjoint paths. So we will define the edge capacity function to give a 1 for any edge, and then we will choose the source and the sink to be the origin and destination. So now we have a valid instance of a max flow problem, and we can solve that max flow problem using our favorite algorithm, say Ford-Fulkerson. The result that we get back when we solve a max flow problem is a flow function, and a flow function is not immediately an answer to the disjoint paths problem. So we have some additional translation to do to take the answer that we got back from solving max flow and turn it into an answer to disjoint paths. In this case, we do that translation by building this graph G double prime, which again has all the same vertices, but now we include exactly those edges that have 1 unit of flow under the flow that we computed. So if the flow function that we got back had 1 unit of flow on all of the edges that I've colored and 0 units of flow everywhere else, then G double prime would have all of the uncolored edges removed. And because each of these edges had a flow of 1 and a capacity of 1, it should be the case that if we start by following some edge from the origin, we should be able to find a path all the way to the destination along these flow edges. So we'll perform a depth-first search, which will give us some path from the origin to the destination. Let's suppose that we followed these 2 red edges and then these 2 green edges. We will delete that path from G double prime, and we will add it to our collection of disjoint paths. If there was a cycle in that path, it's not helping, and so we could remove it. But then we'll keep going as long as there are any out edges from the origin. So next we might find this path, add it to our collection, and remove it. And finally we would find this path. And so we've returned a collection of 3 disjoint paths, and on the graph we were given, that was the best we could do. But how can we prove that this reduction algorithm is correct on any graph? Well, we need to show that the number of paths that we produce from the flow is exactly the maximum number of disjoint paths in the original graph. Since we want to show that the number of disjoint paths in our original graph corresponds to the number of paths that we can extract from the flow, let's define variables for the number of paths and the value of the flow. So the first thing we want to prove is that the number of disjoint paths in our original graph G is equal to the value of the max flow in our translated graph G prime. We can show that these are equal by showing inequalities in both directions. Because we built G prime to contain all of the edges of G, except for the useless ones that come into the origin or out from the destination, we know that any path from origin to destination in G is also present in G prime. So if there were P disjoint paths in G, there must also be P disjoint paths in G prime. And each of those paths can carry 1 unit of flow, so there must be a max flow of value at least P in G prime. In the other direction, if the flow in G prime is F, then that means that the outflow of the source is equal to F, and since all of the edges have capacity 1, that means that there are F different out edges from the source carrying flow, and so we have F different out edges from the source, or the origin, when we build G double prime. And for each of those out edges from the source, we know that the flow will be conserved, and so that flow must go somewhere for every vertex it enters until it gets all the way to T, which means that for each of those out edges of the source, we have a path that goes all the way to t. Then, since each path that comes out of the origin eventually gets to the destination, and it cannot use any of the other out edges of the origin because the source has no in edges in G', we must use up exactly one path from the origin to the destination on each iteration of this while loop, and that path will use up only one of the out edges of the source. So we find a number of paths from origin to destination equal to the value of the flow. So we've now argued that the max flow in G' is equal to the number of disjoint paths in G. And along the way, we also argued that our while loop doing repeated depth first search finds all of those paths, and because every time we find a path we delete all of its edges, we know that the paths we find will be disjoint, and so what we return is a collection of disjoint paths whose size is as large as possible, so our algorithm correctly solves the original disjoint paths problem. Up next, I'd like to show an algorithm that uses reduction to a linear program to solve a problem that we've seen before. Our problem here is finding a shortest ST path in a weighted graph. We've talked about several variations on this problem where if there are no negative edges, we could run Dijkstra's algorithm, or if there are negative weight edges, then we could do dynamic programming. But in this version of the problem, we are allowing negative weight edges, but we are not guaranteeing that there is a finite solution. We allow that there might not be any path from S to T, in which case we should return that there is no path. And it might also be the case that there is a negative weight cycle along some path from S to T, in which case the cost of the minimum path is undefined. Our algorithm works by building and then solving a linear program, and that linear program has a variable to represent the distance of each vertex in the graph. Perhaps counterintuitively, we will be maximizing the distance to vertex t, but we will enforce via the constraints that this variable cannot take on a value larger than the cost of any path from S to t. And so by maximizing subject to those constraints, we will get a value for this variable that is equal to the weight of the min-cost path. The constraints we need here are that the distance of the start vertex is 0, and for every edge in the graph that goes from U to V, we will constrain the distance of that edge's destination. We enforce that the distance to V is less than or equal to the distance to U plus the weight of the edge. And since we have a constraint like this for every edge in the graph, we will potentially have multiple constraints upper bounding the distance of any given vertex. So for example, if the vertex V has 3 in-edges, then there will be 3 different constraints on its distance. And so jointly, these 3 constraints will enforce that the distance to V is no more than the smallest of these 3. And so as long as the distance to U, W, and X turn out valid, they will correctly constrain the distance to V along each of those paths. Once we have translated our shortest path problem into a linear program, then we can run our favorite algorithm for solving a linear program to get a value for each of our variables. And of note, If we are trying to design an algorithm with guaranteed polynomial runtime, we should not use the simplex method to solve the linear program, because the simplex algorithm has worst-case exponential running time. But there are other algorithms that can solve linear programs in guaranteed polynomial time. So in our algorithm description, we could solve the linear program by one of those. But in practice, if we were coding this algorithm, we would import a library for solving linear programs and just set up our linear program in the format that that library expects, and then call its functions for solving a linear program. Many linear programming libraries will actually run the simplex algorithm and other guaranteed polynomial time algorithms in parallel, because it turns out that the simplex algorithm is often quite fast in practice, but we want to have the guarantee that we won't take exponential time in the worst case. But once we get back a solution to the linear program, if it succeeded, it will give us a value for every variable, which we will interpret as a distance for every vertex. But it's also possible that the linear programming library will tell us that our LP was infeasible, there was no way to satisfy all of the constraints, or it might tell us that our linear program was unbounded. That is, when we maximize dv, it might go off to infinity. So we should think about what it means if this linear program is infeasible or unbounded. Starting with unbounded, the reason that there might be no finite upper bound on the distance to v would be if there is no chain of constraints that connects this distance to our constrained distance of 0 for the start vertex. And that corresponds to no path in the graph existing from S to t. If we have a graph like this, then the distance to this vertex is constrained by its relationship to S, and the distance to t is constrained by its relationship to this vertex. But since there is no chain of constraints from S to t, we could make this vertex's distance arbitrarily large, and likewise t's distance arbitrarily large, which would give us an unbounded maximal value. On the other hand, if we have a path from S to t, then t's distance is constrained by the distance to this vertex, which is constrained by this one, which is constrained by S, and so now there will be a finite upper bound on how large the distance to t can be. So if our LP solver tells us that the objective is unbounded, then we conclude that there is no ST path, and therefore we return none. But what about the case where our LP solver tells us that the program is infeasible? In that case, we are returning undefined, which means we are concluding that there must be a negative weight cycle in the graph. So let's take a look at a graph with a negative weight cycle and think about why that results in a linear program that is infeasible. In this graph, we only have 2 vertices and 2 edges, and we'll consider 2 variations on this graph where the back edge from t to s has either a weight of 2 or a weight of -2. When we build the linear program for this graph, we will have a variable for each vertex. So we will have a ds variable and a dt variable, which means we have a 2-dimensional linear program that we can actually draw. When we write down the constraints for each of the edges, we will have one constraint on dt and another on ds. For t, its in-edge comes from s with a weight -1, so we constrain that its distance is less than or equal to s's distance -1, and by translating this to standard form, we can make it easier to draw. So this constraint intersects the horizontal axis at 1, and the vertical axis at -1. And since the origin 0, 0 does not satisfy this constraint, it is forcing us to be on this side of the line. In the case where the edge from t to s has weight 2, then our constraint on s is as follows. And we can translate that to standard form and read off the intercepts. We hit the horizontal axis at 2 and the vertical axis at -2. And in this case, the origin does satisfy the constraint, so we need to be on this side of the line. And in this case, we have a feasible region between these two constraints, so it is possible to find values for ds and dt. When we also add in the constraint that the distance of the start vertex is 0, that actually forces us to be on the vertical axis. And so our feasible region is just this line segment here, and the optimal value for the objective comes when we set dt equal to -1, which is in fact the cost of the minimum path from s to t. On the other hand, if the t to s edge has weight -2, then instead of the purple constraint, we get the following. And by translating to standard form, we can read off the intercepts. We cross the horizontal axis at -2 and the vertical axis at 2. And here the origin 0, 0 does not satisfy the inequality, so we are on this side of the constraint. And so if we combine the green and red constraints for the -1 and -2 weights, then we get an empty feasible region. And that makes sense because if the weights are -1 and -2, then for any finite path cost, you could find a path from s to t of smaller weight by going around the cycle enough times before you stop at t. So in the case that the linear program is infeasible, that's an indication that the distances to the vertices are not well defined because there is a negative weight cycle that can make the distance arbitrarily small. And so in that case, for our original shortest path problem, we should return undefined. To prove the correctness of this algorithm, we need to formalize the intuitions that we've developed from these small examples. And specifically, we need to show that we are correct when we return undefined or none, and that if the linear program does give us a valid answer, then we have the right path cost for vertex t, and so our procedure of tracing back from t to see where the costs came from gives us a valid path of minimum cost. First, we have our argument that t is unreachable if and only if the linear program is unbounded. So here, instead of showing unreachable if and only if unbounded, we are arguing the contrapositive, that t is reachable if and only if the objective is bounded. And that comes from the fact that we have a finite upper bound on t exactly when there is a sequence of inequalities connecting s to t. And since each inequality corresponds exactly to one edge in the graph, we have a finite upper bound on t if and only if there is a sequence of edges in the graph from s to t. For the negative cycle case, we can think about what causes the linear program to be infeasible, and that happens when there is a sequence of constraints that forces the distance of v to be greater than the distance of u, and the distance of u to be greater than the distance of v. If our constraints force du to be strictly less than dv, that corresponds to some path of negative weight from dv to du, and likewise, if they force dv to be less than du, that corresponds to a path of negative weight from du to dv, and so a sequence of constraints that makes the linear program infeasible corresponds exactly to a negative weight cycle in the graph. In the event that the linear program is both feasible and bounded, our objective, where we maximize dt, will force the distance of vertex t to be as large as possible, subject to the constraints, and those constraints will enforce that the distance to t is no more than the cost of any path to t. Each path from s to t in the graph will constrain how large the distance to t can be, and so the smallest of those upper bounds will be the result that we get when we maximize t, meaning that the value of dt will be equal to the cost of the shortest path. And by a similar argument, all of the vertices that are reachable from S will have their distances similarly constrained. And so all of the vertices along this path will have their value equal to their cost on the path. And so if we trace our way back along the vertices that have the right costs, we should be able to reconstruct the path that constrained our objective, which gives us a minimum cost path from S to t. I hope this has given you a sense of how we can design algorithms by reduction. We have a new problem that we can solve by reducing to max flow, and we have a new algorithm for an old problem by reduction to a linear program. Of note, if we have another algorithm for solving a given problem, that's usually more efficient than the reduction to a linear program. And so in practice, I definitely recommend that you not apply this algorithm, but rather find shortest paths using Dijkstra's or dynamic programming. But for designing new algorithms, if you don't know of a way to solve them, but you can translate the problem into a linear program, you now have an algorithm. And so reductions to these types of optimization problem are an extremely powerful algorithm design technique.